Large language models are essentially very large transformer networks trained on enormous corpora using next token prediction objectives. In speech processing, deep learning models often combine convolutional front ends with recurrent or attention-based sequence models. In reinforcement learning, deep neural networks serve as function approximators for value functions, policies, or world models. The unifying theme across domains is the use of deep parameterized functions trained end-to-end from raw or minimally processed data. Another important idea in deep learning is end-to-end learning. Traditional pipelines separated feature extraction, modeling, and decision logic into distinct handcrafted stages. Deep learning encourages collapsing these stages into a single differentiable system optimized jointly. This often yields better performance because intermediate representations are optimized directly for the final objective rather than for proxy tasks. However, end-to-end learning also introduces new engineering and scientific challenges. Debugging becomes harder because errors are distributed across many layers. Interpretability is more difficult because learned features are not human-designed. Training can be computationally expensive and energy-intensive. Dataset quality becomes critically important because the model will faithfully learn biases and noise present in the data. Scaling laws have become a central empirical observation in deep learning. Across many domains, performance improves predictably as a power law with respect to model size, dataset size, and compute. This has motivated a shift toward very large models trained on web-scale data. At the same time, scaling introduces practical concerns such as memory bandwidth, distributed training stability, and inference efficiency. Distributed training is often necessary for modern deep learning systems. Techniques such as data parallelism, model parallelism, pipeline parallelism, and sharded optimizers allow training to scale across many GPUs or accelerator devices. Communication overhead and synchronization become significant bottlenecks, requiring careful system design. Another dimension of deep learning practice involves pre-training and fine-tuning. Large models are often pre-trained on massive generic datasets using self-supervised objectives. They are then fine-tuned on smaller task-specific datasets. This paradigm has proven extremely effective because the pre-trained model captures general structure in the domain, reducing the amount of labeled data needed for downstream tasks. Self-supervised learning deserves special attention. It refers to training objectives derived from the structure of the data itself rather than from external human labels. Examples include masked language modeling, contrastive learning in vision, and next token prediction. Self-supervision has enabled training on enormous unlabeled corpora, which are far more abundant than labeled datasets. Optimization in deep learning is typically non-convex, meaning the loss surface contains many local minima and saddle points. Despite this theoretical complexity, simple first-order methods often work surprisingly well in practice. Empirical evidence suggests that many local minima have similar performance in large networks, and stochastic gradient noise can help the optimizer escape sharp minima. Generalization in deep learning remains an active research area. Classical statistical learning theory predicts overfitting when model capacity greatly exceeds dataset size, yet deep networks often generalize even in highly overparameterized regimes. Hypotheses involve implicit bias of gradient descent, flatness of minima, margin-based explanations, and data manifold structure. Another important practical concern is inference efficiency. Training may happen once at great computational cost, but inference must often run millions of times in production. Techniques such as model pruning, quantization, knowledge distillation, and efficient architecture design aim to reduce latency and memory footprint while preserving accuracy. Deep learning systems are also sensitive to data distribution shifts. A model trained on one distribution may perform poorly when deployed in a different environment. This has motivated research into domain adaptation, robustness, out-of-distribution detection, and continual learning. Real-world deployments must account for monitoring and retraining pipelines to maintain performance over time. Ethical and societal considerations have become increasingly important as deep learning systems are deployed widely. Issues include bias amplification, fairness, privacy, energy consumption, and potential misuse. From a technical standpoint, this has spurred work on differential privacy, federated learning, interpretability tools, and alignment methods. From an engineering perspective, building deep learning systems involves an entire stack. At the bottom are hardware accelerators optimized for tensor operations. Above that are numerical libraries and deep learning frameworks that provide automatic differentiation and GPU kernels. On top of the framework sit model architectures, training loops, data pipelines, and evaluation infrastructure. At production scale, one must also manage model versioning, monitoring, and continuous integration for machine learning systems. The success of deep learning should not obscure its limitations. These models often require vast amounts of data and compute. They can be brittle under adversarial perturbations. They may fail in systematic ways outside their training distribution. Interpretability remains limited compared to symbolic systems. Research continues into hybrid approaches that combine neural networks with structured reasoning or external memory. One conceptual way to think about deep learning is as differentiable programming. Instead of writing explicit rules for solving a task, we define a parameterized program whose behavior is shaped by gradient-based optimization. This viewpoint emphasizes that neural networks are flexible computational graphs that can incorporate many components, including attention, memory, routing, and even differentiable simulators. As the field progresses, there is increasing interest in efficiency and sustainability. Training frontier models can require enormous energy budgets. Researchers are exploring sparse architectures, mixture of experts routing, low-rank adaptation, and more efficient training curricula to reduce resource consumption while maintaining performance. Another frontier is multimodal deep learning, where models jointly process text, images, audio, and video. These systems learn shared representations across modalities and can perform tasks such as image captioning, visual question answering, and cross-modal retrieval. Architecturally, multimodal models often combine modality-specific encoders with shared attention-based fusion layers. Evaluation of deep learning systems remains nuanced. Simple accuracy metrics often fail to capture real-world usefulness. Robustness, calibration, fairness, and safety properties must also be considered. Benchmark-driven progress has historically accelerated the field, but overfitting to benchmarks is a known risk. Despite the rapid pace of innovation, many foundational principles remain stable. Deep learning relies on large parameterized nonlinear functions, gradient-based optimization, large datasets, and hierarchical representation learning. The specific architectures and training recipes evolve, but these core ideas continue to underpin modern AI systems. Looking forward, research directions include better theoretical understanding of why deep networks generalize, more efficient training algorithms, improved robustness, and tighter integration between learning and reasoning. There is also growing interest in continual learning systems that can update incrementally without catastrophic forgetting. In practical terms, mastering deep learning requires comfort with linear algebra, probability, optimization, and software engineering. But perhaps more importantly, it requires an experimental mindset. Many breakthroughs in the field have been driven by empirical iteration guided by intuition about representation and optimization dynamics. Deep learning has transformed computer vision, natural language processing, speech recognition, and many other domains. Yet it should be viewed not as a finished technology but as an evolving framework. The field continues to discover new architectures, training paradigms, and theoretical insights. Understanding the fundamentals, hierarchical representation learning, differentiable computation, and large-scale optimization, provides a durable foundation for navigating whatever architectural innovations come next.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.